Let's move on to the next talk. We have Dr. Jason Picardo. He's an assistant professor at the Department of Chemical Engineering at Indian Institute of Technology, Bombay. He's also an alumnus. He did his PhD from IIT Madras on several different problems, I think, including some of the living systems and so on. So today he's going to talk about turbulent flows. Over to you, Jason.
Thank you, Sumesh. Can you see my slides changing?
Yes, we can.
Okay, perfect. Thank you. So let me start by wishing you, Bala, a very happy birthday. I had the opportunity of meeting Professor Balachandar the first time when I visited Florida as a PhD student. And I remember discussing my work. He was there at a presentation I was giving, and I really appreciated that chance to talk to him about my work. Since then, we've met a couple of times. It's really a pleasure for me to be here and to talk about some recent work on the scission of polymers in turbulent flows. So this work has been done in collaboration with Dario Vincenzi in France at Nice, and Shamruddhi Shankar Ray at Bangalore at ICTS, and Takeshi Watanabe at Nagoya Institute of Technology in Japan. And I'd like to acknowledge funding from IIT Bombay's IRCC seed grant. Okay, so why are we bothering about the breakup of polymers? So let me begin with a couple of experiments just to highlight why this is a particularly interesting problem. So the long-standing interest in the dynamics of polymer solutions stems from the fact that when polymers are in a flow, they experience fluid drag, and that can stretch out the polymer. And the feedback that results from the stretched polymer back onto the flow modifies the flow and leads to quite dramatic phenomena, one of which is the well-known drag reduction or Tom's effect. Another of relatively more recent interest is the elastic turbulence. Now, in both cases, the origin of this is the stretching of the polymer. But the flip side of this is if the polymer is stretched too far, it can snap mechanically and break up, what we term scission in this talk. So here is a very telling experiment done in 1993 by Musa et al., which shows you both phenomena together. So these authors measure the friction factor in a pipe at different Reynolds numbers. And in this plot, you see the top line here is the Glacius equation, which gives you the Newtonian drag or the Newtonian friction factor. And you see the polymer solution has a dramatic reduction even for ppm level concentration. This is basically the drag reduction effect. That is dominant at Re less than 10 to the 4 in this plot. But as you go to higher Reynolds number, which means as the fluid gradients are getting stronger and the polymers are getting stretched to a larger extent, the drag reduction does decrease initially following Work's maximum drag reduction asymptote, which is like a theoretical limit for this phenomenon. But beyond a certain Reynolds number, you start to lose this effect. And this loss, and you see that the drag is increasing once more, that is really due to the breakup of these polymer molecules. And the reason this happens is when they break up, they form smaller fragments, and these smaller fragments have a smaller relaxation time, or their effective spring is stiffer. And as a consequence, at a certain point, they can no longer be stretched, and you lose this phenomena. You basically start recovering a Newtonian behavior. Another experiment, which is more akin to the simulations I'll be showing you, is this double gap geometry, where you have this inner annular cylinder being stirred by a motor. So you apply a fixed torque and you measure the angular velocity, and that gives you a drag or a friction factor. And now if you look at that level of drag reduction, again for different Reynolds numbers, and these results are by the group of Suarez. They did it for different polymers as well. And the common feature you see is that after of course, this is with time now because it's a fixed kind of batch experiment. So after an initial time, when the polymer is able to stretch out, it creates this drag reduction. So the extent of drag reduction increases initially. But then at later times, the polymers start to break up and you get this slow decrease. Note the logarithmic scale of the time axis. So the decay is relatively slow, but you can see it's quite prominent. And eventually you almost lose the effect entirely. So those are, I mean, by way of motivation. Now, it's also a very interesting problem because it's kind of an outstanding open question at the interface of complex fluids and turbulence. So if you just look at laminar extensional flows, there's lots of work that has been done on the scission of polymers in simple extensional flows. And this paper here by Suresh Kumar's group is a particularly good one, which gives a very detailed model of the process using Brownian dynamics. So this is well understood. But if we now look at turbulent flows, there we have experiments like the ones I showed you, but there are almost no models. And so there's really a lack of understanding, theoretical understanding. And that's pointed out in this editorial by Suarez in Journal on Non-Newtonian Fluid Mechanics. There is one model, a valiant modeling attempt based on a phenomenological continuum description, again by Suarez's group. And you see that if you look at the gray curve, they're able to capture some decrease in drag reduction, but then they get these wild oscillations, which they say are just numerical artifacts. So it's our belief that the way to resolve these issues and properly capture this phenomena is to go down to the molecular scale where the scission event is actually taking place, right? So that's what we're going to do in this. That's the focus of our work, where we combine Brownian dynamics of relatively simple polymer models in full DNS and study the breakup of polymers individually and look at their statistics with the hope that what we understand from there could ultimately be taken up to a continuum description. Okay, so I'm going to talk about these three things today. So first, I'll start with passive polymers, which are basically very dilute polymers that do not feed back on the flow. And I will just see the one-way coupling of how the fluid causes them to break up and study some of the properties of that scission. And we'll also just look at the first scission event. So you have a molecule and it breaks up the first time. So we just study that as a first step. Then in the second part of my talk, I'll take it forward to see how after the first breakup event, it undergoes successive breakups if I allow the simulation to carry on. And then that allows you to kind of answer long-time questions about the final population of polymers you are left with. And finally, I will allow the polymers to feedback on the flow. I'll also have to take a lot more polymers to get it a bit more concentrated. And that should allow us to capture the loss of drag reduction, and maybe we'll understand something useful from that. Okay, so let me start with the model, both for the polymer and the flow. So for the polymer, we use the standard Finney model. So it's basically, if you direct your attention to the schematic, it's a bunch of beads. Each of these beads would have been like a tracer experiencing fluid drag, except for the fact that we've linked them together by elastic links. And these elastic links have a finitely extensible spring law, so that there's a maximum stretch Qm, where Q is the extension of each individual link. In addition to this, I have a Brownian noise acting at each of the beads to represent thermal forces. And yeah, if you look at the equation here, you have this gradient of the velocity, which is accounts for this fluid drag that tries to stretch out this molecule. Now, the most important thing is if I have, let's say, a collection of such links, each of these elastic links have a well-defined elastic time scale tau, which is just related proportionally to the spring constant. So I can set this value and it's basically a constant. But the question is, if I have, let's say, 10 of these links, then what is the effective relaxation time of the whole chain? So that is quite well described by this mapping, which was first introduced by Jin and Collins in DNS. And I can discuss the physical background to this if you're interested in the question answers. But the key thing to note is you see that as you increase the size of the chain, the effective timescale increases, right? So tau chain is the timescale of the whole object and tau is the timescale of each link. So this means if I have a larger chain, it's going to be easier to stretch with the same fluid drag force. On the other hand, if the chain breaks up, then the daughter fragments would be harder to stretch. And that really is the physics that we want to capture. So that happens naturally in our model because we are using this sort of scaling. And so with this tau chain, I can define the Weissenberg number of the whole object as the elastic relaxation time of the whole molecule divided by some fluid time scale, which I will talk about in the next slide. We also account for extruded volume and hydrodynamic interactions between the beads. Again, I can comment on this if there is interest. Okay, so this is the flow. We create a turbulent flow in a periodic box using standard pseudospectral simulation of the Navier-Stokes. So we pump a constant amount of energy into the large scales via stochastic forcing. The result eventually is that we have a stationary turbulent flow where the amount of energy we pump in gets dissipated through viscous effects. So we have this fixed dissipation of energy epsilon. Now, based on that, I can define the Kolmogorov length and time scale. So initially, one might think that you could use a time scale as a characteristic inverse strain rate that the polymer would experience. But actually, a better quantity is not that. So the reason you can see here, if I plot the local dissipation experienced by a polymer that moves through this fluid, you'll see a very erratically fluctuating intermittent time series, right? Because the polymer is navigating through the flow, and this image on the left is actually the regions of intense strain. So it's quite intermittent. So a better time scale is actually the inverse Lyapunov exponent. So lambda is the Lyapunov exponent, and it goes as about 0.151 over tau eta for our simulation. Because this basically characterizes the exponential separation of 2 points in the fluid that start out close together at long times. So it's really an appropriate quantity for polymer stretching, and this has been studied in detail in past work. So now we can define our Weisenberg number as the Lyapunov exponent multiplying the time scale of the chain. So the main thing to remember is for large Weisenberg means I have a molecule that can stretch to a larger extent, and one would expect such an object to break up faster. So that's something to keep in mind. Okay, so another important point is why the scission events are different in turbulence compared to laminar flows. So if you look at the coil stretch transition, right, in a laminar flow, so you put a molecule in an extensional flow and you start increasing the Weisenberg, which I'm doing here. And then you look at the PDF of the extension. So R is the end-to-end extension of the chain. You see that for small Weisenberg, all the polymers are coiled. And then as you increase Weisenberg, they do stretch out, but they stretch out as a group. So the PDF remains sharply peaked and simply translates. But in a turbulent flow, because of this chaotic nature of the strain rate that is experienced, you see a dramatically different kind of stretching out behavior. And the PDF becomes much broader as it undergoes the coil stretch transition. For us, the critical Weisenberg of the transition is 0.5 based on our definition. So this is in the linear scale. If I take the y-axis to a log scale just to show you how things are happening more clearly, you see that there is really a broad sequence of broad distributions that are formed, and ultimately the peak shifts from coiled to fully stretched out at very large Weisenberg. But in between, you really have a broad distribution. And indeed, in a log-law scale, you see that they are described by power laws. And this again has been studied before. So the main message I want to convey is that the behavior, the stretching out behavior is very different in turbulence, which is why it really merits a separate investigation. Okay, so the final point of the model is how do I implement scission? So because I have this chain series of links, it's quite easy for me to do it in a precise way within my simulation world. So whenever any of the links stretches beyond a threshold, I break that link, and the remaining 2 fragments are my daughter fragments, and then I can continue to follow them and repeat this process. And so I just set the scission length to be about 80% of the maximum possible stretch in this simulation. These details don't affect the results. Okay, so let's look at the first scission event, which tells us something about the onset of the degradation. So I'm going to plot how the number of unbroken polymers decays in my simulation, and these are 10 bead chains. So you see that on a semi-log plot, you get these nice straight lines indicating an exponential decay of the number of unbroken chains. And I can extract out a timescale from here. You see that if I plot that timescale versus Weisenberg, there's a dramatic decrease as I cross the coil stress transition of 0.5. Right? So that's what one would have expected. And it's really a very clear exponential decay. So whence this exponential decay, we can get some insight by analytical theory. So what we do is we can use just a dumbbell model and replace the turbulent flow field with a Kraichnen random flow. So we just have a Gaussian fluctuating velocity gradient for every chain. And then you can write a Fokker-Planck equation. And it turns out that this equation, we include scission through the boundary conditions by setting the probability distribution to 0 at the scission length. So it turns out this is just a linear operator, it's Sturm-Liouville, and it has orthogonal eigenfunctions. And because the number of unbroken polymers is just the integral of this distribution, if I just take the leading eigenmode, I just get this exponential decay behavior. And if one carries out this calculation, you can understand the dependence of this decay on Weissenberg, and all this matches well with our simulations. Okay, so let me now go to the repeated breakup of chains. So basically, I'm going to follow the daughters as they break up. Again, the key thing to keep in mind is as my chain undergoes successive breakups, the effective timescale of the daughters will decrease because n is decreasing, right? So quickly, let me show you some results here. So the first case, I'm starting with a 10-beat chain, which has an original Weissenberg of 0.8, quite small. So what happens here is only the parents, which are shown by the dark with the black line, decay. It forms a range of daughter molecules, but none of them decay. Then if I increase Weissenberg progressively, you start seeing that around 2, the 5 beads that are found, which is this red curve, they also decay. And if you compare the decay rate of the red curve with the parent black curve, you see that the 5 beads decay much more slowly, which is again consistent with the fact that they are stiffer, they don't get stretched out as easy. So is there a way for me to estimate the effective Weissenberg of a daughter and therefore understand whether it's going to break or not? Well, once again, we can go back to our mapping, which if I represent it in terms of the parent Weissenberg, I get this ratio. So N0 is the number of beads in my parent molecule, N is the number of beads in the daughter. And using this and the fact that if I'm below the coil stretch, I expect it not to stretch out and therefore not to break, I can make some predictions that work quite well. So for example, if I take a parent of Weissenberg 4, which is this final plot D, I can say that a 4 bead will have a Weissenberg that is greater than half, so it will not, so it will break. That's what you see here for the orange curve. But a dumbbell will have a Weissenberg smaller than half, it will not break, and that's what you see with the blue curve. So it does seem to work well. Okay, and the nice thing about this, I'm almost out of time. So the nice thing about this is there are these experiments that were done by Vanapalli and co-workers in 2006, where they took 2 different geometries of rheometers and passed polymer solutions through them successively until the distribution stopped changing, and they measured the contour length of the surviving polymers versus Reynolds number, and they got a nice scaling. And it turns out that from our simulations, we can actually explain that. Because again, if we say that the daughter Weissenberg, which has survived at the end of, if we wait for long enough time, the surviving polymers Weissenberg should be less than Weissenberg critical, then I can use my relationship here. And I can relate tau eta to the Reynolds number and n square to the contour length. And using Kolmogorov phenomenology, what I get finally is that the contour length L square should go as Reynolds to the -3/2. And that's exactly this solid line. So it does seem that this simple timescale reduction with breakup seems to capture what's happening in these experiments. Okay, so finally, let me just quickly talk about feedback of the polymer. So we do that by including a polymeric stress into the Navier-Stokes. And this is a plot of the dissipation volume averaged versus time. So you see that at early times, you have a reduction of dissipation from the Newtonian value, which is just 0.5, shown by the horizontal line. So there is a reduction in all cases of the Weissenberg. But then as time proceeds, this loss of dissipation vanishes, and we ultimately get back to the higher Newtonian value. And the timescale over which this loss happens corresponds exactly to the timescale over which our molecules break up. So we are able to capture this loss of, in our case, dissipation reduction, since we don't really have a drag without walls. And the important thing to note here is that if you look at a small Weissenberg, its maximum dissipation reduction is less, but it lasts for a long time because they break up more slowly. But the large Weissenberg case, which is 0.1, it actually loses the dissipation reduction effect very fast because it breaks up quickly. So if you really want to maximize drag reduction or dissipation reduction in a time integrated fashion, then you should go for an intermediate Weissenberg. Okay, so to conclude, drag reduction, dissipation reduction, it owes its origin to polymer stretching that we understand well, but it also meets its demise due to polymer scission. And this same phenomena I've described here of scission would be relevant even in elastic turbulence, although we expect different behaviors because the elastic turbulence itself will decay as the polymers break up, unlike the case I described here, where actually you get a stronger turbulence back. And finally, we are hoping in the future to use some of these insights to develop continuum models, and then which would be useful to study more complex situations like shearing flows. Okay, so with that, I thank you for your attention. I'll be happy to take questions. And our work is out in this paper if you want to look at some other details.
Thanks, Jason. We could take a couple of questions for Jason. We also have a break till 8. So I'll also invite Professor Kumaran to join the session in case there are questions for him. So Jason, when you defined your Weissenberg number based on this Lyapunov exponent, how do you sort of what is the physical meaning of Weissenberg number then?
Yes, so it's still the ratio of the relaxation time to the time scale with which it gets stretched out by the flow, really. So the Lyapunov exponent basically tells you that if you have 2 points close by, that they would stretch out as e to the lambda t. So it's roughly the time scale it would take for the polymer to get stretched out if there were no elastic force, if you like, and that is kind of pitched against the stiffness of the spring that gives you the elastic time scale. So you would get qualitatively similar results even if I used let's say the Kolmogorov timescale or any other timescale in the turbulent flow. Right. But it's just that this particular choice gives you a particularly nice transition, and we can compare it to some theoretical work.
Okay, I see. Right.
So for example, here you see that as I cross around 0.5, which we expect to be theoretically the transition, you see that these straight lines, the slope of the straight lines change quite dramatically across 0.5. 0.5, 0.6. So yeah, that is just for that. Yeah.
Okay, right. There's a question. Yeah.
Just one comment, Jason, great work. I just couldn't stop comparing some of these results that you're showing with something I recently read on flocculation dynamics, where instead of chains, they have flocculation of primer particles. And instead of elastic thing, they have sort of bioadhesion and adhesive forces. So you might look into that. So thank you very much.
Well, that's very interesting. Thanks, Bala.
Yeah. Jason, there is a question in Q&A. This is about the length scale of the polymer molecule with respect to the Kolmogorov scale. What is it?
Yes, yeah. So it's all smaller than Kolmogorov scale in our simulations. Yes. So basically, the polymer just sees a linear velocity field at any instant of time, but that velocity gradient, of course, fluctuates chaotically as the polymer moves through the flow. Yes, thanks for that question.
Right. Any other questions for Jason? Okay, so if there are no more questions, I think we can wind up this session. Let's thank Professor Kumaran and Dr. Jason once again for the wonderful talks.